Okay, so it was very hard to focus on preparing these slides in the last couple of days, but I promised Hatim to deliver this webinar, so here I am. Today I'll be talking about supercomputing software for more and beyond. I hope this presentation will be informative for you. You can learn something and I can learn something from you. I would like to start with a brief history of Moore's law. As you know, Moore's law begins in 1965, and today we are marking it 60 years of innovations thanks to the Moore's law. And I'll be talking about a lot of innovations happening between these 60 years, but mostly focusing on the last 20 years or so, mainly because I started working in this area around 2005 and 6. But if you are wondering what happened in between, like in the first 40 years or so, I highly recommend looking at the Turing Award lectured by Jack Dangara. So let's talk about what Moore's law is first. Moore's law is the observation that the number of transistors in an integrated circuit doubles every 2 years or so. So we started, like, if you look at the last 20 years, there was a transistor with feature size of 130 nanometers. And then over years, we have seen shrinking the feature size and reaching 5 nanometer. This just happened incredibly fast in the last 20 years, resulting a lot of innovations and technological advances. But we are, with the speed of light and the atomic nature of the materials and the growing cost of manufacturing, unfortunately, we are marking the end of Moore's law. Especially the manufacturing cost has increased drastically in the last couple of years. For example, to manufacture a 5 nanometer chip, you have to pay $500 million. And for specialized chips, this can be even higher. So this was kind of the dark side of, like, kind of the sad end of Moore's law. But thanks to Moore's law, we had a lot of improvements and innovations as well. And in supercomputing, we like to, mark the milestones of every achievement of gigaflops to teraflops to petaflops. So in 1985, we had the first gigaflop machine, which is Cray 2. Cray 2 can achieve 10 to the 9 operations per second, can perform 10 to the 9 operations per second, which means 1 billion operations per second. This can be seen to be an enormous number of operations, but actually today we have much capable machines doing much more than that. So in 1998, we had another milestone, which is the first teraflop machine. There is a question in the chat. Oh, okay, sorry. So in 1998, we had the Red ASCII, which is the ASCII Red, which is the first teraflop machine achieving 10 to the 12 operations per second, which is 1,000 times more. And 2008, with Reordering, we were able to reach petaflop scale computing, 10 to the 15 operations. And last year in 2022 with Frontier, we were able to perform billion operations per second. That's 10 to the 18 operations per second. So this is kind of the milestones for supercomputing. But in terms of general public, actually, the current cell phones or laptops they are capable of doing teraflop operations, 1 teraflop or 2 teraflop. This is incredible. This is incredible increase in innovation, because you can basically supercomputer size machine from 1998, you can put in your pocket thanks to Moore's law. So there are two observations coming from this innovation, and one of them is we can actually do supercomputing on a desktop. What does that mean? This Moore's law will democratize the supercomputing. So if you're a domain expert, you can of course do more things on a supercomputer, but it also allows you to do modeling and simulation on your laptop or desktop, because technically you have access to a supercomputer from 1998 on your laptop. If you want, you can also do this on a cell phone. So in fact, I was listening news the other day, and an earthquake expert was talking about simulation they are doing at the 500 meter resolution on a workstation. And he was mentioning that we weren't able to do this 10 years ago. The workstation cost him $25,000. This seems a lot. It's a lot actually, but it's still comparable. I mean, compared to the $250 million supercomputer. Of course, there are more things you can do on a large-scale supercomputer, but thanks to Moore's law, we can also do supercomputing on a desktop, meaningful simulations on a desktop. The other observation, which is I think not that pronounced in our field, is HPC software that we develop and my group develop or other groups develop eventually will make it to the cell phones or laptops or general public. This gives me a leap and makes me happy, because I'm not just developing the software to maybe, may I say, small group of people, but whatever I develop, optimizations or frameworks or tools, within 15 to 20 years, they will make it to general public and massively used in these laptops, and maybe influence the design of the software in those machines. Okay, going back to this last, the innovations or trends in the last 20 years or so, I would like to start with the first trend, which is multi-cores. In 2005, we started seeing multi-core architectures. This is now ubiquitous. We have multi-cores everywhere. We had a fat, big core, but now we have small mini cores. One thing, though, we initially predicted that the core count will double every other year or so, but that didn't happen. The core count doesn't increase as much as we expected. It's still in the orders of tens, in some cases hundreds, but it's not in the order of thousands in a multi-core architecture. And the other thing that I would like to emphasize is teaching multi-core programming, because it's so ubiquitous, it's everywhere. I think we haven't really even though our efforts to integrate into our curriculums and teaching schedules, etc., we should start teaching multi-core a lot earlier, maybe at the same time as we teach programming. I consider this as, because multi-core is not going anywhere, it will be around. I think we should teach multi-core a lot earlier in undergraduate programs. The second trend that I would like to talk about is the heterogeneous computing. I consider this an inevitable ending or alternative to multi-core. Around 2010 or so, we saw the first GPU-based supercomputer, which ranked #1. And then in successive years, we started seeing several solutions in the software, like OpenACC, OpenMP, adapting offload model. And then in this last year, we had the first exascale supercomputer, which consists of AMD GPUs. So there are several solutions how to program an accelerator, particularly GPUs, but multi-GPU still support is not fully there, and we would like probably more research in multi-GPU programming and have more solutions in that area. And I also consider the GPU-based supercomputers as an alternative, but not the only solution. We have a good example, for example, Fugaku machine, which ranks number 2, and it's a homogeneous architecture. So the third trend I see is the emergence and dominance of AI. Honestly, we didn't expect this in HPC. We didn't see it coming. 2016 and onward, AI really dominated both the market and basically all the trends. So parallel training is the new norm for deep neural network training, and they will probably shape how architectures will look like in the future and how the software will adapt to them. So there are things that we should learn and probably have more interactions with the AI community. The fourth trend that I would like to talk about, data movement cost. I consider this problem as unsolved, even though we have attempts. We spent several years addressing data movement issues, communication issues, but I consider this problem is not solved yet. So to explain the problem, what I mean with the data movement cost, I will explain first energy and the performance problem. So the first is, let's say we want to compute A plus B. We have a core and we have a memory, and this causes some data locality issues. If we typically have these values A and B in memory, this memory can be cache or memory or even off chip. So a very, very conservative estimate, this operation costs 100 picojoules, like A plus B. But only one of them, 1 picojoule, is spent in addition operation. The rest is spent in the control and data path. So that really tells us the computation is extremely cheap to do compared to data movement. So our focus is really should be on the data movement and optimizing data movement. We see this also in terms of performance gap in imbalance machines, compute speed versus the memory bandwidth improvements over the years. So you see here, can you see my cursor, by the way?
Yes.
Okay. So this is years, and this is basically compute speed divided by the bandwidth, which is flops divided by words. Most machines, today's machines are clustered here in the right upper corner. That means today's machines are capable of doing 100 flops per word transfer. They can do more computation than even we need to. But however, applications are mostly memory bandwidth or memory latency or network bandwidth bound. That this causes machine imbalance, and this also leads to increasing gap between the data movement speeds and the computation speeds. This was actually very apparent in high performance conjugate gradient performance. This HPCG benchmark is used to rank supercomputers in addition to LIMPAC benchmark. LIMPAC benchmark is doing the dense linear algebra benchmarking, and this is, we can consider representative of sparse linear algebra, representative of sparse solvers. If you look at this last column, we see that how the percentage of the peak performance achieved by this benchmark. And this clearly shows the machine imbalance that today's supercomputers, they're not very good at solving sparse computational kernels. and they are harder to scale and optimize, and they are bounded by the memory network bandwidth and latency. So I'm wondering, when will CG be able to sustain exaflop performance? Because right now it's around performing petaflop performance, not an exascale performance. So it will require at least 100x performance improvement over the years. So there is a hope, though. If you look at AI community, they're also sparsifying things. So there's a trend there for sparsification, because over the years they wanted to have larger, bigger, more parameters in a model, but then they started looking at model sparsification for inference and training, and then start designing hardware acceleration for sparsity over the years. So maybe the solution may come, or we may benefit from the innovations in the AI community for the sparsification. Even though their sparsification is slightly different than ours, still there might be lessons to learn from that community as well. Okay, if we wrap up what I have just talked about, data movement still dominates the performance and energy consumption. In this case, because the flops are very cheap, hiding communication cost will become increasingly difficult, but it will be necessary. And at the very high level of parallelism, synchronization becomes increasingly expensive as we increase the number of cores and accelerators in the system. And we should just stop counting flops and count data movements and develop profiling tools to help us understand the data movement in our applications. So with these, acknowledging these dominance of data movement cost and data locality issues, in 2014, we started this workshop series, PADAL workshop series, with a number of people, and like based on these workshops, we gathered our thoughts in a document which is called Programming Abstractions for Data Locality, and a concise version of it we published as a journal article at TPDS. I recommend people to read this document if you're interested in data locality and data movement optimizations. And because of the pandemic, we stopped the workshop for a couple of years, but this year we are reviving it and planning to host it in September of this year. Okay, so next couple of slides, set of slides, I'll be talking about what we do in my group to address some of the challenges coming from sparse computation and the synchronization issues and proposed alternative model of execution, and the data locality tools that we develop in our group. So I would like to start with the Sparsity project, which this is a consortium project with 6 partners in Europe, and we are developing frameworks for sparse computation. So when we say sparse data structures, there are 3 data structures we are mainly focusing on. First is sparse matrices. These matrices contain mostly zeros. So non-zero percentage is like 1 to maybe 1%, around that or less. And there are graphs and sparse tensors, which are, we can maybe safely say that it's multidimensional matrices, 3D, 4D, 5D matrices. So what we are trying to do is we are extracting structural features of these sparse data structures to understand their performance behavior and also design algorithms or tools based on these extracted features. And we actually collected these structural features under this document, core set of sparse computation features. It's available online. I'm showing an example here for sparse tensors. We have a list of features and their description how they are calculated. So where can we use these extracted features, for example, for a sparse matrix? So reordering is a common method for better caching for sparse computation, for example, sparse matrix vector multiplication. And one of the reordering algorithm is RCM. So at the top, you see sparse matrices that are not ordered. Ordering means permitting the rows or columns in the matrix. And in the bottom, this is the reordered matrix by using RCM algorithm. As you see, the speed up varies. You have degradation of performance or improvement, greatly improved performance after RCM reordering. So our goal is, can we use these extracted features to understand, predict, or select which reordering algorithm might help, or whether it's ever going to help in terms of performance or not. So we are using sparse matrix collection, suite sparse, but we consider these collections valuable, but at the same time, they are not enough to do, large studies, extensive studies. So we are also developing a matrix generator, which can be very useful because you can generate matrices with different structural features. And then we have a number of reordering algorithms that we are studying, focusing on, like PADAL, METIS, RCM, Rabbit, AMD, Gray Code, etc. So we implemented all of these and then run through your sparse solver, let's say SPMV in this case. Either we use this and correlate them with the features, or feed it into ML model to understand which features are related to, which reordering algorithm and predict the performance. So similar pipeline we design also for sparse tensors, especially in sparse tensors. Tensor generator plays an important role because there are not many public tensors that we can access, and sometimes they are very big. So creating them on the fly is very useful. And in this case, you can do tensor decomposition as your computational kernel here. And all of these, we have this pre-processing framework that we kind of the umbrella framework that gets the sparse data structure. It can be graph, matrix, or tensor, feeds into the sparse data framework, which performs the pre-processing. So most sparse computation requires pre-processing the data first, like reordering or partitioning for parallelization, or conversion of between different storage formats, or in our case, calculating the structural features. After this pre-processing, we can send this to sparse kernels of your choice that the user implements, like BFS or SPMM or SPMV, etc. So you can access this sparse space. It's open source at this link if you would like to play with it. Okay, next, I would like to talk about our CPU free execution model. This work is not published yet, but hopefully it will soon. Okay, so traditional GPU execution model, we refer to as a kind of offload model. There is CPU and an application code, and then we identify regions of interest that we would like to accelerate. Here in this case, I marked them with pink, right? So we offload these to the GPU, but how does this work in terms of software? CPU controls the following. CPU controls the compute kernel launches, issues the communication calls, overlaps the communication with compute, acts as the synchronizer. So GPU only performs the computation, but remember my previous slide, computation is cheap, and what is taking more time or is causing more overheads is all the control and issuing these calls and the control logic on the CPU side. So our goal in this model is, can we move, if not all, but some of these control logic to the GPU side as well, so that we don't need to go back and forth between the CPU and GPU. So we came up with this CPU-free execution model, and important components of it are, we are using persistent kernels, which are long-running kernels on the device. And we have thread block specialization, which we spare some thread blocks for communication, some thread blocks for computation. And we issue all data movement on the device side. We don't go to the CPU. And we do all the synchronization also on the device side, including within the device and across device synchronizations. And we implemented this model of execution for Stencil Computation. And as you see in these figures, the blue line is a CPU control, which is a traditional. And then the CPU-free execution is the pink line, which has much low communication overhead compared to the blue line. And the second figure shows how we can do a better overlap if we do this on the GPU side completely and reduce the overall execution time. And we also implemented this same CPU-free execution for conjugate gradient, both for standard conjugate gradient and pipeline. I'm not going to go to details of the difference between these two, but it doesn't matter for the purpose of this slide. The pink ones are using our CPU-free execution, and these are CPU control, which is traditional execution. And we achieve over 60% improvement with the CPU-free execution on various sparse matrices that we tested. So while developing the CPU-free execution model, we realized that also data movement, when issued on the device side, is not really tractable, or it's not easy to monitor if you use NVIDIA's profiling tools or other profiling tools that are out there. So we decided to develop our own profiling tool just to monitor data movement between multi-GPU devices. So stay tuned on this. We are still working on this profiler. So speaking of the profiling tools, we have a number of data locality tools as well for multi-core. And some of them, I listed them here. The first one is ComDetective. This is a lightweight communication detection tool for threads. And second is Reuse Tracker, which is a reuse distance analysis tool, again, for multi-core. While developing these tools, we basically developed these tools for Intel and AMD, and we realized there's a huge difference in their PMU precise event sampling supports in these architectures. And then did an extensive study, AMD versus Intel. This study is very important for people who are designing that hardware component, or people who are developing profiling tools to understand the profiling tool behavior on AMD or Intel. So I'll briefly talk about these. And if you want to learn more about this, you can contact me later. So ComDetective is this tool that detects inter-thread communication. So in the literature, there were some tools that detect communication between processes and like MPI communication, like EasyTrace, etc. But there were no tool detecting the communication between threads within multi-core. So we developed ComDetective that creates these communication matrices and also differentiate them true sharing and false sharing. True sharing is actual communication between threads, that is intended communication. False sharing is due to the cache coherency protocol, or those two lines or two elements of a happen to be in the same cache line, so it's not intended communication. So we can detect both with the COM detector. And the reuse tracker is a reuse distance analysis tool, which can be used in loop transformations in a compiler. This is one of the first, it's the first tool that does reuse analysis, both private and shared caches, and also detects cache line invalidations. So where can you use these tools, or how? COM detector can guide the thread to core binding. So if you have multi-threaded applications and you want to bind these threads to cores, you can extract communication metrics and do the binding based on that, or it can be used for code restructuring to remove false sharing in an application. And we did this and observed 13% improvement by eliminating the false sharings in data structures. And the reuse tracker can be used for loop transformations that will be implemented to improve locality, and decide whether to activate some of the hardware optimizations, such as cache line prefetching, etc. So both tools are available in our repository, Parkour Lab, under the Tools tab. Okay, so I'm wrapping up. So in terms of outlook, I think the future of computing is exciting because we are about to end the Moore's law. For some people, it's already ended. Some maybe a couple of years, or they are ahead. But parallel systems are here to stay, and we will have both homogeneous and heterogeneous systems. And the reducing data movement and synchronization overheads are crucial to achieve good performance. If we look at the post-Moore's era, I think it requires more interactions with vendors and AI community to solve the data movement problems, and HPC can help AI, and AI can help HPC. And I see that there are a lot of research opportunities in this field, and we are hiring if you are interested. My last few words are, I consider supercomputers mean really superpower, and by developing software for supercomputers, we can control that superpower. And I would like to use this superpower for disaster management or large-scale earthquake simulation. So this is an open call for collaboration. I believe with the help of HPC, we can do ground motion prediction, create detailed seismic hazard maps, and do very high resolution spectral acceleration measurements. I'm sure there are experts out there, for example, in Japan, or in I know that in San Diego Supercomputer Center, there are experts there as well. We can collaborate on the structural infrastructure support, simulation, modeling, parallelization support, and we can leverage domain experts from other countries. So you can reach me about this issue, this topic, via my email or Twitter. I'll be happy to, start this collaboration as soon as possible. Okay, thank you very much, and I'm happy to answer if you have any questions.
Great, thank you so much, Didem. Thanks for the great talk. So I'll just post it on the chat. The link for the survey for those who are here at the webinar. So let's see. We have one question from Nesreen Kouzami. Did you ever consider in-memory computation to alleviate the communication overhead?
That's a very good question. Actually, we were looking at in-memory computations. I contacted with UpMem about their architecture, memory solution. But if you know other in-memory computation that we can access, because I found it's a bit difficult to access the real hardware. Maybe people access, simulators or prototypes, but it's not that easy. I've contacted UpMem for this, and we may start working on in-memory computation as well. But if you know other sources, other alternatives that we can readily use, that I'll be happy to look at those. I think it has a potential to reduce this data movement overhead.
Thank you. We have another question. So let's see. How do you feel about democratization of supercomputing in the near future? It seems supercomputing, when it comes to those new AI models, at least is very dictatorshipy. Do you think they will become democratized again in the near future?
Well, so I understand the kind of the frustration of people when accessing machines. We sometimes have this issue as well. So we have access to node like a workstation or a laptop, etc. But if you want to go beyond, it's very difficult to access such machines, even though some countries give you some cycles to experiment, but especially, and these cycles are limited, right? You can run experiments, let's say, a couple hours a day for an entire year. For AI workload, that's impossible because the training takes so much time. So I cannot speak for AI models. I understand your frustration, but I guess I cannot help with whether this democratization will happen for the AI models or not. I think this is a big problem that, only big companies have the resources and capacity to run big trainings.
Maybe a follow-up question on this. Do you think supercomputing scale heterogeneous systems will become more affordable and available in consumer products?
Well, supercomputer scale in near future, I don't think so, because the cost of designing, I didn't mention, maybe I mentioned, but for example, GPU design costs like $2 billion. So I'm not sure whether how many countries will have access to these. In Europe, actually, because not a single country cannot have such a large machine. They are creating consortiums. So 10 countries combine their efforts to build an exascale machine. In Europe, this may be possible, but I cannot imagine this is happening in other parts of the world.
Thank you. A question from Ligang He. What is the main difference between sparseness of AI operations and sparseness of HPC operations?
Yeah, that's a very good operations. Good question. So in AI, people tend to use SPMM, which is sparse matrix matrix multiplication, but also the sparsity level is in AI is kind of dense compared to HPC sparsity. So let me give you an example. In HPC, our matrices are like 1% dense, but in AI, 10% dense is already, like 50% is already sparse. So it's between 50 to 10% sparsity. So that's the, their matrices are more dense than ours, basically.
Good. Two more questions, I guess, and then so from Muro, has there been any research on defining a new type of compute engine that improves inter-compute engine communications as well as improving data movement?
So it's a good question. There are actually a lot of projects that I'm aware of from Europe, like e-processor that's prototyping a new type of processor, and there are chiplets, many projects coming up, more on the hardware side, designing more data movement aware or data-centric chips, not worrying about too much about the flops, but worry about more the data movement.
Okay, and perhaps the last question from Filippo Onerato. The trend to put neural engines, CPU and GPU and memory on a socket on chip like Apple is doing seems now established. How do you see it evolving?
Yeah, so we can, so in HPC, initially we thought we will have a lot of heterogeneity, but it was already a big headache to have one type of accelerator, which is GPU. But it might be inevitable to see these chiplets where you have, let's say, instead of neural engine, you may have neural engine because in HPC, there are a lot of deep learning workloads as well. People start using deep learning in applications. In addition to that, we may have bioinformatics engine, for example, Stencil engine, or sparse graph engine, etc. So it's possible. The programming, it will be extremely difficult. I think while designing chips, people should consider how people will program this, because it's not sufficient to design an efficient chip. But I remember cell processor. I spent a year in my PhD. It was a nice piece of architecture, but it was very difficult to program, and it just disappeared. So it shouldn't happen. When people design chips, they should consider how people will program and provide software stack for programming.